Very good afternoon, everyone, and thank you very much for joining us today. My name is Nikhil Vaswani, and I'm a junior consultant at Turner & Townsend, and today we're very kindly joined by James Treehen, Regional Technical Manager at Structherm. This is a retrofit information, support and expertise event, which is fully funded by the Department of Energy Security and Net Zero, and is delivered by Turner & Townsend. This will be a relatively short presentation, followed by the opportunity to engage in a Q&A with James. The event will be an hour long, and we will finish on time. May I please request that you keep your microphones muted and cameras switched off during the presentation. The slide deck shared on screen will be made available after the event in a follow-up email to all attendees. Additionally, there will be a clean recording of this and all other masterclasses in the resources section of the RISE website. Before James does begin, I will share a series of useful links in the chat function, which will take you to our RISE resources. May I also please ask that any questions be posted in the chat function as we go along, or alternatively, should you prefer, you may come on screen after the presentation to ask James questions directly. Finally, there will be a quick poll and word cloud at the end of the session. May I please request that you complete these to help us understand the level of knowledge in our topics. And with that, I will hand over to James for today's presentation on external wall insulation in retrofit. Thank you, and over to you, James.
So in terms of the agenda, we'll be starting, obviously, just giving a little bit of introduction to Structherm and obviously where we fit into the whole retrofit schemes that we're working on in the moment. The history of non-traditional construction in the UK, the problems associated with non-traditional properties, refurbishment of non-trads, introduction to the structural external wall insulation system in addition to EWI, installation, case studies, and then at the end there'll be a summary of the presentation as well as questions. So just a little about Structherm. We've been going for just over 40 years. In terms of products that we supply, design, and in terms of the projects that we're involved in, external wall insulation, renders and finish, and then structural external wall insulation in terms of a unique product to ourselves. So in terms of BBA and KEWA certification, external wall insulation ranges and structural EWI ranges are both covered by those. In terms of the sort of projects we're involved in, low-rise housing, high-rise housing and non-residential buildings. The photo up there of the before and after is an example of a BISF construction. So that's a non-traditional type, which we'll cover a little bit more as the slides go on. So as many of you will be familiar, a lot of external wall insulation projects that have been done over the years are to treat solid wall properties, and cavity wall properties are increasingly having EWI applied to them also as part of a dual function. So they're having cavity wall insulation and EWI. We'll have a little bit more information as to why that's been done further on in the slides. But really, external wall insulation as a measure for solid wall properties has been really quite effective. The main reasons for that is it's done externally. So internal wall insulation can be quite disruptive, and this provides an opportunity for housing associations and councils to address the stock with obviously minimum disruption to tenants. So in terms of your solid walls, obviously pre-1950, pretty much solid wall construction. Cavity walls is when 1935 that sort of started to come into construction, but as things have changed over the years, it's a multitude of different sort of cavity walls that you'll find now. So you'll find block and brick, some will be brick and brick, and it's all sort of multitudes. And the way that things have moved on, you'll find that a lot more modern buildings will be a mixture of timber frame as well as a brick skin on the outside. So the history with non-traditional buildings, obviously after World War II, there was a bit of a change in the actual construction sector. So there was a shortage of brick manufacturers as well as actual labour in terms of the actual skilled labour and brick layers to put the actual houses up. So as the war effort, looked to diversify away from the factories that were supporting the war effort, a lot of them then got involved into building houses. So stuff like the BISF, which was the British Iron and Steel Federation, they designed the BISF house, which was done in a few different archetypes. But generally, it was a need to construct buildings quickly, and obviously they didn't always think of the long-term solution. So some of them only had a design life of 30 years. A couple of examples of the different types of non-trads that you'll come across, particularly in terms of housing associations and council stock. So a lot of these properties were built by councils and housing associations, and therefore a lot of them do remain within their housing stock. They are some of the harder properties to deal with, and the main issue with that is the structural condition. So BISF properties are one of the ones that fall into the steel frame category. You've got Boswells, Aries again, they sort of fall into the PRC, so they're a concrete frame structure with concrete panels on the outside. The cross walls are a bit of a later addition, so they are what are classed as RATTRADs, or rational traditional construction. So they're a little bit later than the non-traditional construction, and the idea with RATTRADs was you would build traditional construction masonry walls as your gable end and your party walls, and then you would have timber factory panel made constructions then shipped in, transported on site and just dropped in on the front and rears. In many cases they're non-load bearing on the front and rear, they're just infill panels. So the four types of non-trads in terms of category is timber frame, precast concrete, metal frame and in situ concrete. The timber frame properties, there's over 142 of these specified by the BRE, and in terms of information and sort of identifying timber frame properties, it can be a little bit more difficult. The main reason for that is they're externally clad with a multitude of different finishes, and when they were originally constructed, you may find that they've gone through refurbishment projects where they've had the original cladding taken off and then replaced with something else. So trying to identify the type of timber frame non-trad you're dealing with can be quite difficult. In terms of the solution for non-trads, the metal frames, for example, the BISF, which what the 3D graphic is there showing, is the steel frame structure with the sheathing rails and the wrinkly tin cladding at the first floor level. At the ground floor, the structure differs again. So instead of the sheeting rails and the wrinkly tin cladding, you've got render on chicken wire mesh that is just pinned back to the steel frame. Again, some of these steel frames have got brickwork on the outside, so true steel is a good example of that. So true steel construction is basically a steel frame that's got a brick skin on the outside, and again, dealing with them is another sort of method that you need a different solution for. So where external wall insulation works for solid wall properties, where the name suggests you've got a solid wall to fixture, with a lot of these non-traditional properties, you'll find that you've either got framed structures or you've got, like the in situ concrete, two leaves of in situ concrete that are typical of a cavity wall construction, in the sense that you'd have block work on your inner leaf and brickwork on the outer leaf. But with the in situ concrete, your usual issue is that you'll find problems with the wall ties between the two layers of the concrete. Another form of in situ concrete that is a non-traditional construction that's probably worth mentioning is no fines construction. So no fines is a little bit better than some of the other non-traditional properties, in the sense that it tends to be around 200 to 250 mil thick of no fines in situ concrete. The problems with no fines is that, as the name suggests, there's no fines within the mix, and therefore it's quite an aggregate concrete mixture. When you put fixings in there, they tend to be able to be pulled out with the hand because they just blow in the actual concrete. We have got a method of dealing with that, in the sense that rather than specifying hammering fixings, you would look to specify STRU anchors. And it's also very important that you do pull-out testing across the properties that you'd be looking to address. The main reason for that is the nature of no fines concrete is that the mix of the pour is always a little bit random to a sense. So the people who have been mixing and pouring the first couple of houses on the street when they were being constructed might be a different mix to what you find later down in the other streets, that where there might have been a different group of labour working on them properties, or it might have been just they've actually got a better mix as they've gone through the construction phase. So doing the fixing pull testing on properties by property basis is quite important for us, just to make sure that we can ascertain how many fixings are going to be required to hold the EWI system back to the wall, and making sure that the anchorage is going to work under the wind loads specific to that area. With PRC, the area is a good example, in the sense that that's the 3D that's being shown there. The area constructions are quite a difficult one, in the sense that they're area concrete columns, and then they've got concrete panels that are then tied back to the concrete columns with a wire, basically. So it's just basically copper wires holding them back. The problem with area properties is that they can suffer from carbonation of the concrete. So that's basically moisture is finding its way to the concrete is then carbonating, it then can obviously spore. So we've been to some instances, particularly in the sort of southwestern areas where it's quite wet. They've basically had issues on the western elevation where water's getting behind the concrete panels, travelling down the posts, and basically they've all spalled off, and it's just the tubular bar that's left, and the two halves of the concrete are in the cavity. There are also other instances where the PRC was taken out in the 70s and 80s. So after the BRE had designated the area properties as non-designate effective, basically saying that there were structural issues, they put together a method of dealing with that. So what they did was prop the roof, prop the floors, take the concrete panels off, take the concrete columns out, replace them with a galvanized steel box section, hot dip galv. And then basically once that new section was in, they would then put the concrete cladding panels back on the outside, take the props away, and then you would have your area house back there, but it wouldn't be the concrete columns, you would now have new steel columns. That did work in a sense that it dealt with the concrete column issues, but it didn't deal with any of the insulation problems. The other side to that is some of the schemes that had the concrete columns replaced with steels didn't use hot dip galv, they just used plain box section, and then inevitably the same issue that you would have with the concrete in the sense that water's found its way behind the panels, travelled down the steels, and it's just corroded the base of the steels. One instance that we found, it was just 6 inch of steel work had disappeared, it just corroded, and both of the steels at either side were taking the weight. So it is important for all of these non-traditional properties to undertake proper structural investigations, so structural engineer involvement, ideally structural engineers who have got experience and have dealt with these types of properties in the past. That is becoming more of a problem. Obviously, as the age of the properties increases, the wisdom of the people who are around dealing with these properties is also shrinking. So these are just a couple of examples of projects we've been involved in that are a mixture of both traditional construction and non-traditional construction. So the top left and the bottom right both show non-traditional construction that have had a structural EWI system applied. Both of them have had a mixture of silicon render and art render finishes. The bottom left was originally solid 9-inch brickwork that's then been modernised and had a modern silicon render finish. It's had new roof, solar panels. That was the first project working to PAS 2035 standards in Scotland for Renfrewshire Council. The top right is a project up in Durham, which is solid stone properties. Again, external wall insulation has been able to be used there in terms of using an art brick finish to get a like-for-like appearance. So it's making sure that whichever sort of non-trad or traditional property you're dealing with, it's being able to find a solution that works for that property type. So just going back to just traditional constructions, this is an example of a recent project that we've been involved in. So this is an SHDF scheme in Altrincham. So the client's L&Q for that one. And in terms of the main contractor, it's Waits Property Services. So the top left shows the before the refurbishment, and the main requirement for this project was to specify an EWI solution. Because of the size of the properties, IWI didn't really lend itself, as well as it being too much of an intrusive sort of measure. The other side of it was this is on the edge of a conservation area in Altrincham, and therefore the planners and the client wanted to ensure that they weren't obviously detracting from the local vernacular. So rather than just going with a white silicon render, they've matched the like for like. So they've used the art brick product to replicate the arches, they've used insulated sill profiles to replicate the concrete sills, and they've really gone to town in terms of making sure that they could go down the permitted development route, therefore saving time going through planning, but also being sensitive to the area at the same time. So problems with non-traditional properties, as we've already touched on, the quality and the thickness of insulation is questionable. So with area properties, we've been to sites where we've taken some of the concrete panels off on the outside, and lo and behold, the plasterboard isn't even visible behind the radiator. So you could just put your hand straight to the back of the radiator after you've taken the concrete panel on the outside. They were quick to build, and obviously they had a low cost in the sense that compared to traditional construction with labour shortages, etc., it was an easier and quicker way of getting these houses to where they needed to be. There was quite a few issues in terms of concrete quality, failure of wall ties, as I've mentioned, with some of the in situ concretes, as well as the frame structures. So you might have steel frame that have got a brick skin. That brick skin is tied back to the steel frame, and inevitably the wall ties have failed. And a lot of them did only have a limited lifespan in terms of the design. So a lot of some of the temporary bungalows, it was even in the name that they were always going to be temporary, but some of them were still remaining today. Identifying non-trads, as I've mentioned with the timber frame properties, because of the different cladding types, that can make it quite difficult, as well as obviously when they were originally constructed, a lot of works might have been undertaken in that time. So we've seen BISF properties that have been overclad with weatherboarding, but there's not been any insulation. It's just been an aesthetic upgrade. It might have also been a way to stop water ingress in terms of if they were having problems with the existing cladding. So identifying the properties is really quite important for us as a starting point, as well as the structural engineer involvement. Obviously, if they're able to help identify properties that aren't able to be identified until you actually start poking around and making some holes in these walls, and obviously getting up in the roof space is always a good point. Corrosion is an issue in terms of what some of the problems that can be faced, as we've mentioned with the steel frame properties, and what we've found with some of the issues of corrosion. It is a real thing that needs to be taken into account, particularly if you're going to be putting external wall insulation or even internal wall insulation on some of these structures. If they're not structurally sound, the last thing you want to be doing is applying additional weight. So that's an example of a column base that's suffered from corrosion and it's actually cracked. In terms of lintels and timber frame decay, again, there are other points that need to be checked for, as well as the actual primary frame of the structure. It's making sure that the secondary members that are doing stuff, such as obviously supporting the loads above the windows, etc., loads above your doors, are in an adequate state, because the last thing you want to be doing, as mentioned, is applying additional weight to a structure that's already in a state of disrepair, really. So, as I've already touched on, in terms of trying to identify non-trads, the problems is with the existing cladding is the obviously wear and tear. They are aging properties. A lot of these were built in the 50s, 60s, and therefore, you know, they're coming on to 60, 70 years old in a lot of cases. Therefore, the cladding that was always on the outside, BISF steel sheet profile, that's tend to have fared quite well. We have seen it painted over the years and they don't look very clever when that starts flaking, but you know, they do the job in the sense that they keep the water out. Concrete panels on precast, they tend to be the worst in terms of the cladding panels, in terms of the ingress of water. Weatherboarding and stuff on the timber boarding, obviously you can have problems with tile hanging, and it comes with any of these cladding systems. If they've not been properly maintained, you're going to find issues with water ingress. You're going to find issues with parts of the cladding wanting to part away from the building. And we've found issues with some of the precast concrete panels where they're in such a bad state structurally that the actual concrete panels are basically bowing away from the walls, or basically stack bonded, and therefore one of them has fallen down on the other and it's just slipping out of place. So it's trying to identify these properties as well as understanding what condition they're in before we're trying to specify solutions. So as mentioned with the Airy property, that's probably the key one that's on this list, but this list is from the House Act 1985, which obviously put the designated defective clauses together from the BRE. So this is what the BRE had identified as non-traditional dwellings that they would designate as defective, meaning they've got structural issues. As I've already mentioned, we're still here today in terms of a lot of these non-traditional properties. Obviously, anyone who's familiar with the image there of London, we are aware that a number of these dwellings have been demolished, others have been refurbished, and in terms of retrofit, it is a huge scale of what is out there that still needs to be dealt with. So the challenges of non-traditional is firmly upgrading to current regs whilst minimising the risk of condensation. It goes without saying that if you're going to be applying external wall insulation to any building, you want to minimise the risk of condensation and increase the thermal value. Increasing the thermal value is straightforward when you're doing U values for straightforward walls. If it's all solid brickwork all around the building and you've just got your window openings to consider, that's not too bad in terms of actual calculations and making sure that your thermal bridging is going to be okay. When you're into non-trads, you're into a multitude of different wall build-ups. On the same property, you might have different areas of different wall build-up, in the sense that you might have wrinkly tin steel frame upstairs that's got some insulation within the frame, and then downstairs it might be solid construction, in terms of you've just got the render mesh construction, there's no insulation within the frame, and therefore making a starting point as to deciding what you're going to do with that existing build-up. Are you going to alter that existing build-up before putting EWI on it? And if so, what is going to be the risk of condensation or thermal bridging in areas where you're not able to get the same level of insulation? So it's understanding how to address each of these non-trads whilst obviously maximising the thermal value. Improving aesthetics goes without saying that a lot of the non-trads are not very sort of pleasing to the eye. They're a bit drab, concrete constructions. A lot of them have obviously got aging cladding that's decaying or not looking the best. So therefore there is a chance to obviously improve the aesthetics. Ensuring the structure's sound, I've mentioned it numerous times so far, but the starting point for all of these non-traditional properties has got to be a structural assessment from our point of view, understanding what that existing structure is, what's its capability of taking the loads of a new system, how we're going to specify it and fix back a system to that property, because of obviously the different types that you've got, you're going to need different fixing solutions for each one. Conforming to building regs and fire regulations, obviously U values in terms of meeting your Part L. Your fire regulations are obviously very important, and understanding what buildings need an A1 or an A2 rated system, and understanding where you need your fire breaks, etc. And all of that sort of gubbins is very important to be sort of considered as part of the overall package. So understanding how your EWI measures are going to interact with your roofing measures, your window measures, etc. All that needs to be considered. Minimising disruption to tenants is very important in terms of obviously getting people engaged with retrofit. In order for projects to proceed, it needs the tenants to be on board, and ultimately, as even though the client is the housing association or the council that is spending the SHDF funding or the LADS funding, etc., ultimately it's the tenant who is the end client, in the sense that they're the one having the retrofit measures fitted to their property, and they're the one who is going to be living with the changes. So it's important to be obviously bringing tenants on board and minimising the disruption where possible. That goes for both the building side of the work as well as the actual engagement process. So if you've got tenants that are wanting to be kept engaged and wanting to be kept updated on what's going to be happening at each stage, which we've got plenty of examples of sort of projects we're working on where there's tenants who want to be around when certain bits are being done just because they're interested in the actual building work. There's others that obviously would rather not be contacted unless they really need to be contacted. So understanding how the tenants want to be engaged with these projects is very important. And completing work in a cost-effective way, again, it goes without saying. A lot of these projects require different measures, and understanding what's the best way to deliver a project in terms of cost as well as quality, and making sure that the project receives what it requires in terms of specification, and making sure that that can be done, that is achievable for obviously the end client, and that works to the funding mechanisms that are currently available. So the options for insulating properties, you might be aware of IWI, internal wall insulation, and cavity wall insulation. Both offer obviously their benefits and their disadvantages. IWI, the main disadvantages is obviously the loss of living space and the sort of having to do the works inside the property. So obviously, as I've just mentioned with the tenants, that engagement process is important, and the last thing that people want is obviously somebody taking all the wallpaper off and putting IWI in, then having to redecorate and obviously disrupting the kitchen and bathroom spaces. But the upside to IWI is that it can lend itself in certain situations. So if you've got rear extensions, or if you've got conservatories, etc., and you're doing an EWI scheme, you might do EWI to the front elevation, rear elevation, and the side elevation. But when it comes to the conservatory space, you would do IWI in the sense that it would be within the conservatory, but you will be obviously applying the wall insulation externally to the wall still. So there are details like that where you can get continuity of insulation when you've got conservatories on the rear of properties. It's just using a mixture of EWI and IWI sensibly. Cavity wall insulation, as I mentioned at the beginning of the slide, solid wall and cavity walls can be treated with EWI. The benefits of using EWI with cavity wall insulation is it addresses some of the disadvantages or some of the drawbacks of CWI. So if you're living in rain exposure zones, which are obviously quite high, so Scotland, the northwest of Manchester area, etc., up on the Pennines where I am here, South Wales and sort of like the Westernly Wales areas, it's a lot wetter than what you get in the east and the southeast, for example. And therefore, if you've got cavity wall insulation applied to them buildings and you've got any issues with your pointing or your bricks are porous, etc., then you can have issues with your CWI having moisture in it and obviously getting wet. That then leads to it being more of a thermal bridge than it would be without any insulation in there. So the advantage of using EWI and CWI together is that obviously it gives you an increased U value, but it also gives protection to the CWI in the sense that the EWI has a waterproof render finish on the outside that is then going to protect the CWI from getting wet. The other side of that is when you're applying EWI to cavity wall insulation, cavity wall structures that don't have insulation in them, it's important that you're blocking off the head of the cavity and any openings that are going to cause thermal bypass or the risk of chance of thermal bypass occurring in the cavity, which is basically when cold air is moving in the cavity behind the EWI system, so that downgrades its effect. So EWI, for anybody who's not familiar with external wall insulation, is effectively insulation layers with a render coat and base mesh. So basically you've got your insulation that's fixed back to your structure. You then got a render coat with your mesh layer, which is what provides the strength and its impact resistance. And then you've got a finish of choice. The render finishes tend to vary, and we'll touch on them a little bit later in the slide. So is EWI the obvious choice? As I've already touched on, I don't think so, in the sense that it's not always the go-to solution. In some cases, as I've mentioned, there's a mixture and there's an approach that works best depending on what the scheme is. So if you've got the luxury of being able to do a mixture of CWI and EWI and getting increased thermal value, it also means that the EWI system can be slightly thinner than what it would be if you had no insulation within the cavity. So it's being able to make these choices and obviously understand what's required for each project. So this is an example of an EWI installation process in terms of V4, getting the insulation boards, base coat, the mesh embedment, the base coat for layer for the second layer, and then your top coat finishes. So then we're finished in the silicon and brick finish on these particular properties. So as I've already touched on with IWI and EWI, there can be instances with IWI and CWI, sorry, there can be instances with EWI where there needs to be additional works done to make it suitable for EWI. Otherwise, you're going to have issues. So as I've already mentioned with the structural engineer, making sure that a structural engineer is appointed and understands the structure and understands the loads of the building, like you don't want to be putting the additional weight on, etc., if that external leaf is going to want to part away from the primary frame of the structure. Likewise, ensuring that the actual substrate can be fixed. So solid wall properties, as I've mentioned, with EWI that can become mechanically fixed as well as adhesively fixed if required. That's perfectly easy to do in the sense that you can do a fixing pull test into the brickwork, and the brickwork is going to tend to be, fairly consistent across the wall. When you're with non-traditional properties, it's the fact that you don't have a solid wall to fixture, and instead you've got a framed structure that's got an infill of some sort, and that infill in some instances might only be 50mm concrete panels, which are not going to provide you a wind load, a pull load, in the sense that the fixing test will just go through the concrete panel, spoil the back of the panel, and you'll be able to pull the fixing out with your hand. So the structural EWI system differs to standard EWI in a sense that the EWI is formed within a wire frame cage. The Warren trusses are what give the cage its structural rigidity and its strength. So the structural EWI system is used for non-traditional properties as well as high-rise properties where standard EWI isn't a viable solution. So the structural EWI system is able to span, and it fixes differently to how a standard EWI system fixes. We've also used it for reconfiguring building facades. So if you're doing high-rise buildings, we've used it for enclosing balconies and walkways, and we've also used it for forming new and extending parapets when you get to the very top lift of the high-rise. So as the EWI and structural EWI differs, the main thing with the existing substrate is how that is going to work. So if you think of EWI as a tea cozy, in the sense that it's wrapped around the building and it keeps it warm, the structural EWI can be analyzed, well, seen as a bit more of an EWI system that's got a tea cozy with a corset on, in the sense that it's holding the building tight and basically stiffening the structure up. It's just gone back a slide there, but we'll just go to the fire performance slide. In terms of fire performance, the classifications on the side there from A1 through to F give you the combustibility. So A1 being non-combustible, A2 limited combustibility, and then B through to F are classed as combustible of different descriptions. The classification is the smoke emission during combustion and then the production of flaming droplets, which gives you an overall classification code. So for example, A2S1DO would be the classification code of a mineral fibre EWI system that's got a silicon render finish or a brick render finish, for example. So this summary is the insulation summary. So as an actual just an insulation product, mineral fibre, mineral wool, rock wool, also known as stone wool, is an A1 insulation. So that's high-rise buildings as well as any low-rise buildings that require an A1 or an A2 system. With phenolic, that's a B-rated in terms of an actual incident starting, and then your graphite is an E. So I don't think that's right on that slide for whatever reason, it hasn't pulled through properly. But and the next slide seems to have missed. Seems to have been a slight issue there. But the next slide would have usually been the classifications. So that would basically break down what they perform as a system. So your phenolic and your EPS insulation systems would perform as a B rated system. So that would be the B1S12S1DO. So that is basically a B rated fire classification for EPS and phenolic rated insulants. And then with the mineral fibre, you can achieve either an A1 or an A2 rated system, and that will depend on what finish is utilised. So A2 rated mineral fibre EWI systems are silicon render finishes, brick and pec render finishes, some dash render finishes. In terms of A1, it's capable of getting an A1 rated mineral fibre system with what is known as mineral render. Mineral render is different to silicon render in the sense that it needs an additional paint layer. So that's the only downside of going to A1 with the mineral render finish, is that it requires an additional painting coat. The other thing that needs to be considered for that is long-term maintenance. So you don't want to be going and painting it in 10 years with a paint that falls outside of the fire certificate, because then it would invalidate that fire certification for that product. So it's very important when specifying and putting forward a system for buildings, particularly high-rise buildings, that you understand what EWI system is required in terms of regulations, as well as the long-term maintenance for that EWI system. So it might not always be best to specify A1 because it's got the best rating, because there is long-term maintenance issues that need to be accounted for, and therefore A2 might be a better solution. But again, it's taking it on a case-by-case basis is what's required. So the accreditations that are shown on screen there are the BBA certifications for the structural EWI systems, and there's additional accreditations and certifications for our range of EWI systems as well. In terms of installation, the structural EWI is similar to EWI in how it's fixed, but there's a few slight differences. So the base trim is fitted at DPC level, as it would be with a standard EWI system. The panels are then cut and locate, so Structherm provide a system panel layout drawing for most projects we're involved in, so that structural EWI project would require a panel layout drawing, and that's basically the best way to orientate the panels, whether stacking them vertically, standing them horizontally. Because they're 2.4 by 1.2 meters, they're able to span in different ways depending on what the existing structure is. So because of all these non-trads having different centers of the columns or having a different actual wall build-up, it's been able to adapt the structural EWI location of the fixings. So the way the fixings are fixed back on the structural panel is different to EWI again. So EWI fixings are fixed through the insulation. So you put the EWI insulation board against the wall, and then the fixing goes through the insulation and into the structure. The structural EWI differs in the sense that because the insulation is held within the space frame wire cage, and that's the part of the system that's giving it its spanning capability, that's where the insulation is removed. That's basically cut out in a square with a pad saw. The fixing is then fixed at the rear of the cage, and that goes straight back into the structure. So that reduces the cantilever effect on the fixing, and it allows the insulation to be then put back over the fixing head. So you don't get the point loss through the fixing that you'd usually get for the thermal transmission through the insulation. Next, it's all meshed together, and then it's base coated and rendered up, ready for the finishing coats. In terms of high rise, as mentioned with the structural EWI panel, it can differ in how it's applied. So the structural EWI panel for high rise buildings is fixed differently. So what we would do is fix a channel at every floor slab. The reason for that is on high rise buildings, when you can't fix a standard EWI system, it's generally down to the infill panels not being well fixed back to the frame. So with concrete frame high rise buildings, you've got concrete floor slabs, which are nice and solid. But then in between there, you've got a multitude of different infills. So there might be a concrete panel that's fixed back to the floor slab and fixed at the head and the base of the slab. The others might be no fines concrete that's been infill poured in between the slabs, and therefore when you're doing the fixing testing, it might not provide adequate loads for standard EWI. So the structural EWI allows you to avoid having to fix into that infill on the high rise and span, basically just fixing at the channel at the floor slab level, and then spanning and avoiding that infill. Your fire breaks then fitted all the way at your fire breaks are then fitted all the way through on your C channel at floor slab level, and then similar to standard the low rise application, it's all panelled, meshed together, and then rendered up and finished. So a couple of examples of sort of before and afters of different sort of non-trads. So these are Swedish Timbers and We Are Multicon timber frame properties. Both of these up in Scotland, where we do quite a lot of work in terms of our overall delivery. So that graphic there shows you how the structural EWI fixes back to the primary frame of the structure. The advantage is that you're putting the loads back to the primary frame rather than on the external cladding. So if you were fixing EWI and trying to fix it to the external cladding panels, you would then be obviously risking the external cladding panels parting away from the primary frame. So that shows you there on a timber frame structure as well, how it's worked. So with steel frame, BISF is a good example. I'm not sure why that clicked through as it did. Let's see if we can go back one. The BISF is a good example. So that's the steel frame upstairs with the wrinkly tin, and then the chicken rendered wire mesh downstairs. So that's an example there of an external wall insulation system being used for the BISF property. Again, metal frame. It's the structural EWI being able to use to fix back to the primary frame of the structure. So you're using the structural panel to span over the existing steels and then fix back through. You've got the option there of either retaining or removing the existing cladding panels. So depending on what measures you're doing, you might want to infill that frame prior to putting the structural panel on the outside. You might find that the wrinkly tin has obviously started to degrade in areas and rust away or fail, etc., in terms of actually parting away from the sheeting rails, and therefore maybe getting rid of it prior to putting the structural cage on is part of the project scope. But you've got the option with the structural cage to obviously adapt it as to what needs to be done for that particular project. So a couple more examples of before and afters with the Boswell properties up in Liverpool. Again, in situ concrete, so the slight difference there is that you're able to use a wall tie fixing. So the structural EWI uses a fixing that goes through both leaves of the cavity, so it basically acts as a wall tie as well as the external wall insulation. A couple more examples there, Boots and Cornish properties. And in situ with the areas, again, precast concrete, so the graphic shows a different type of precast, whereas the graphic on the right shows the area panels. So again, with these precast concrete structures, there's different types of precast. So some of them are precast panelized constructions, and others are the actual columns themselves that have got cladding on the outside, like the area. So the high-rise graphics there showing what I was mentioning earlier when showing the installation. So the spanning of panels going between the floor slabs and therefore avoiding the infill, should that be suspect and not be able to be fixed up with standard EWI. Can also be used to span horizontally from column to column, which is quite effective when you're trying to deal with schools or different smaller frame structures. So we deal with a lot of class schools in this way, and it's also allowed us to reconfigure the window openings, etc. An example of the high-rise building is the Coatbridge project there. So that was a mix of standard EWI and structural EWI. So on the far end gables, they were brick cavity construction. They needed some additional wall ties, but other than that, they were pretty good, and therefore standard EWI was able to be utilised. On the front and rear elevations, they were Siporex blockwork that was in between the floor slabs. The structural engineer on that particular project had a look at the Siporex, did some fixing testing, and concluded that it wasn't adequate to fix to, and therefore the structural EWI system was required to span it over the floor slabs and avoid having to fix into that infill panel. The system had previously had a rain screen cladding system on, and that too had avoided fixing into the infill, instead spanning from floor to floor and then having a cladding panel on the outside. So using the structural EWI allows you to address some of these issues that standard EWI won't be able to get over, really. So in terms of finishes and colours, silicon render, I'm sure everyone's quite familiar with now. The look for the past 10 years seems to have been white render, grey windows. It seems to be ever popular. In terms of dash render finishes, it doesn't tend to be specified as often. So dash render finishes are a mixture of a render finish with an aggregate that's then thrown into the render. The upside to dash finishes is that they're a little bit more hard wearing. And therefore, obviously, they can take a little bit more of a beating than silicon renders. If you're obviously in a high traffic area where the silicon render is obviously going to be getting brushed down by bins on a daily basis, or something that's obviously going to cause risk of damage to the render, then the dash might be a better solution in some cases, where it's going to provide you a bit more of a long lasting and a bit more of a robust finish. We tend to joke around in the office, particularly with our Scottish counterparts, that they cover everything in batter, including the houses. So in terms of dash finishes, that's one that the Scottish tend to use a lot, and particularly because of the weather up in Scotland, looking for a more hard-wearing, robust finish is the way forward, really. In terms of brick effect renders and brick slips, again, there are other finishes that are offered in the market. So brick effect render, anyone's not familiar, is a monotone brick in the sense that you've got two colours. You've got your mortar colour and you've got your face colour, and that's scribed out to provide a brick finish. Brick slips, again, that's another option in the sense that brick slips can be used as an EWI system finish. Tend to be specified for ground floors of high-rise buildings quite a lot, in the sense that they provide good fire resistance, as well as they're a bit more of a robust finish to the silicon render that would be on the floors above the ground level. In terms of art brick, that's a finish that's bespoke to ourselves, and this has been on the market for a number of years now, and basically addresses some of the problems that you would find with standard brick effect render or brick slip finishes. So standard brick effect renders, as I've just mentioned, are monotone in colour, so you'll have a brick colour and a mortar colour, but the art brick allows you to use a series of tints that can provide different multi-stock effects, so it can achieve the same look as a brick slip without obviously having to go to the expense or the impracticalities of install of the brick slip. So a couple of examples here show more projects that have used the art brick finish. So it's also being used for stone effect, as well as replicating features, as shown on the L&Q project. A couple of examples there show the art brick finish in stone effect. So the bottom left one there is the Orbit Housing Association. So we've been assisting Orbit from the SHDF demonstrator phase all the way through to what is now their current wave 3 phase that they've got their bid in for. So in terms of getting a solution for EWI where you might have a conservation or planning issue, then it's always good to be able to offer a like-for-like solution using the finish. And that's it really in terms of the actual presentation slides. I think that one was slightly out of order on the last one, but that's it. Just thank you for your time. If you've got any questions, I'd be happy to help.
Thank you very much, James. And that was a really insightful presentation on EWI, its history, uses, and application in current retrofit projects. Before we move into the Q&A session, I'm just going to launch a quick poll, which I'd appreciate if everyone could kindly take a moment to complete. And that should be on everyone's screen shortly.